Okay, so now we'll see isentropic processes are characterized by several equations that will allow us to easily solve the problems where we have isentropic processes. So first, whenever you have the case of isentropic process for air, okay, you can use reference values of pressure and specific volume to determine, let's say, unknown of state 2. What do we mean by this? So if I tell you, for example, air is undergoing an isentropic process from state 1 to state 2, you can automatically say that I can relate the ratio of pressure P1 over P2 to a ratio of reference. Okay, what do we mean by this? So we'll see that in the table of air, for each temperature, you can define what we call a reference pressure and a reference volume, specific volume. So we can see them here in the table. This is the table you have, okay? You know that for air, at any temperature, you can read the enthalpy value, the internal energy value, and S0. And if you remember, we used S0 to determine the integral Cp over Tdt. Okay, so this is why they put for you S0. Plus, if you have isentropic case, you have the following column. So when delta S is equal to 0, you have a column for reference pressure and a column for reference specific volume. Okay, this means that whenever you have the case of an adiabatic isentropic process, what is the difference between adiabatic and isentropic? When we say an isentropic, it's adiabatic plus reversible. Okay, and Q is 0, and we have that a reversible process, so delta S is 0. Then you can use the following values for PR and VR. And how you can benefit from this, whenever you have, let's say, air undergoing, and please, just for air, and this table is just for used for air. You can say whenever you have air and you have ideal gas properties, you can write directly P2 over P1 equals to P reference 2 over P reference 1. How we can benefit from this? And for example, if you have a problem and you know that the process is isentropic, okay, this means that delta S is 0. You can say P1 reference, okay? You can say directly then, if I know, let's say P2, for example, okay, P2 and P1, and I want to determine, let's say, the temperature T2, for example, okay? So suppose that you have P1, T1, you know P2, and your unknown is T2. You want to determine what is the value of T2. To get T2, you say the following. You say first, I have that P2 over P1 is equal to PR2 over PR1. And since you have P2 over P1, you know this ratio, okay? And because you know T1, what can you get from the table? You go to the table, let's say for a temperature T1, for example, 290 Kelvin. You say, what is PR? You determine the value of PR. Okay, once you get PR at T1, you replace it here. What will be the only unknown then? The only unknown will be PR2. Once you get PR2, you go to the table and you get T2, and you do it in a reversible way. Now we'll do an example. Okay, so always when you have isentropic case for air, you should think about using this formula to get your unknown. Example. If you have the following, okay, just before the example also, you can do the same if you have the specific volumes, okay, because you have not only values for reference pressure, you have also values for reference volume, specific volume. So you can say also that if I know that air is undergoing an isentropic process, so S1 is equal to S2, I can write the specific volume at state 2 over specific volume at state 1 is equal to VRT2 over VRT1. And if you remember, we discussed last time the following relations, okay? And we said that whenever we have ideal gas, we can write the following relation if we consider that Cp and Cv if you want, can be treated as constants. We can take them outside of the integral, and then we get the following. And if not, we can evaluate, for example, this integral from the table by doing delta S 0. Now, how we can find relations in case of isentropic process? If the process is isentropic, this means what? This means that delta S is 0. Okay, so this is equal to 0, and this is equal to 0. So as we discussed last time, whenever you have an isentropic process, you can write the following. You can write 0. Let us consider Cp constant and Cv constant, okay? So from here, you can say that 0 is equal to Cp ln T2 over T1 minus R ln P2 over P1. Okay, so you can say that if I have isentropic process, I can directly say that Cp ln T2 over T1 will be equal to R times ln P2 over P1. And you know from ln properties, okay, if you have A ln B, okay, it's equivalent to ln B to the power A. This is why here you can take Cp inside, and you can write that ln T2 over T1 to the power of Cp is equal to ln P2 over P1 to the power R. Okay, and therefore you can deduce that in case you have isentropic process, T2 over T1 to the power Cp is equal to P2 over P1 to the power R. And since for ideal gas, if you remember, what is Cp? Cp is equal to Kr over K minus 1. Okay, so if you substitute Cp and you simplify R, you get the relation for isentropic process. For the isentropic process, look what you can use. You can use all of these relations. You can say that T2 over T1 is equal to P2 over P1 to the power K minus 1 over K. Okay, and you can deduce this by just applying this rule. And if you replace Cp by its value and you simplify R, you get the result. You can use the same for the second relation and demonstrate that for isentropic process, T2 over T1 is equal to V1 over V2 to the power K minus 1. Here, these relations are characteristics of an isentropic processes. So if you know that the process is isentropic and you know K, if you know, for example, P2, P1, and T1, you can get the value of T2. Let us do an example on these equations. So if we consider air undergoing a process from T1 equals to 620 Kelvin, P1 equals to 12 bar, to a final state where S2 is equal to S1 and P2 is equal to 1.5 bar. They are telling you that employing the ideal gas model determines the final temperature T2 by two methods. The first method is to use PR, and the second method is to assume a constant specific heat K. Okay, so here we'll see that the two methods will give close results. But of course, the first method is more accurate. Why it's more accurate? Because in the second method, you don't know T2. You only know T1. So if you want to assume constant specific heat, you can go to the table of air and look for T1 equal to 620 Kelvin. What is K? Okay, and you will use K as constant, but you know that in reality K is variable with temperature, and that's why method 1 will be more accurate. Okay, let us verify this. So first, what do we know in this problem? We know completely state 1 because you know P1 and T1. while you just, for state 2, you just know P2. You can say, let us do the following. We know that P2 over P1, because it's isentropic and air, and you have the right to say P2 over P1 is equal to P reference 2 over P reference 1. Okay? Now, as we discussed, we know P2 and P1, so we replace. And since we know T1 equals 620 Kelvin, we go to the table. So now we go to the table to get what from table? From table we get PR1. Then the only unknown in this ratio will be PR2. So if we do this, this is our table. We go first to 620 Kelvin. For this value, we read that PR1 is 18.36. So we replace. And then we get the only unknown in this ratio is PR2. Once you get PR2, the value is the following. PR2 is equal to 2.142. So you say, go now to the table and see where is 2.142. 2.142 is between 1.9352 and 2.149. So I can use it. I can say that I will take it between these two values. I do linear interpolation, and I can get exactly what is temperature T2. This is the first method to get T2. Okay? Now, the second method is to say, I will assume a K constant, okay? And since I know pressures P1, P2, and temperature T1, I can say that for an isentropic process, what is the relation between temperature and pressure? T2 over T1 is P2 over P1 to the power K minus 1 over K. So my only unknown is T2. I can substitute and get the value of T2. And you will see that the values are close, not exactly the same, but close. And you know, if you want to enhance your prediction of T2 using the second method, you know what can you do? Who can tell me? If I want to get a better result for T2 using this method, what can I do? نحن مش قلنا انه we assumed K constant and we took K only at T1 because we don't know T2. To have a better estimation of this temperature, what you can do is the following. You can say, now since I have T2, let me update K. I take K average, okay? I can take K average between T1 and T2. So I find the average temperature T1, T2, and then I can determine K at average temperature. This will enhance the prediction of temperature T2. And I can continue to iterate until reaching a satisfying result. Any question on this?
دكتور ما فهمت شو قلتي آخر شي تبع نلاقي كي average.
يلا رح أرجع عيد. نحن when we used this method we assumed K constant, okay? But actually K varies with temperature. يعني for T1 you have a certain value of K, K1, okay? For T2 you have another value of K. And since K is varying from 1 to 2, a good strategy is to say, let me take K at an average temperature. يعني. But once I determine T1 and T2, I can find T average. And what is the average temperature between state 1 and 2? And for this T average, if I go to the table, I can get an average value of K. يعني ما تكون extreme ولا أعلى شيء ولا أوطى شيء. Okay? In this way, you can have a better computation for T2. Because K will be assessed in a better way. يعني أنت إذا K vary from 0 to 100 مثلا أو let's take other يعني logical value. If K varies from 1.3 let's say to 1.4, okay? Instead of taking K only 1.3 or just 1.4, you can say, because K will vary between these two values, let me take like an average value of K between these two. Okay, let us take مثلا K equals 1.35. So, or you compute K1, K2, and you take K average. Or you can also say, I will compute K at an average temperature. And I take the average between T1 and T2 and go to the table to get K at this average temperature. Okay? you try this, you will get T2 closer to T2 from the first method. Because here you got a difference, here it's 345. Here it's 339. You have 6 Kelvin difference. If you try K average, you will get a lower difference between the two temperatures. Now, let us apply how we can use isentropic efficiencies for devices like turbines, nozzles, compressors, and pump. First, what do we mean by isentropic efficiency? Okay, the isentropic efficiency, if you want, will give you the performance of the device relative to the best performance. The best performance, let's say, of a turbine is to deliver work in without having production of entropy in it. We should have a reversible process. When we have a reversible process, what will happen? We have delta sigma will be sigma dot is 0 in a reversible process. And in this way, we'll see that we save energy. Okay, why? Because let us take the example of a turbine. Okay, always keep in mind whenever you solve a problem, first write the energy balance equation, then write the entropy equation to see what are the conclusions that you can make. So, for example, if I take a turbine, for a normal turbine, we consider that if they don't mention anything, we consider that we don't have heat loss to the surrounding. So Q dot is 0. So it's an adiabatic process. Okay, whenever Q dot is 0, it's an adiabatic process. Plus, if we have reversible, and plus if we say it's a reversible process, then what can we say also if it's reversible? If it's reversible, we can say also that we don't have, we'll demonstrate together that this is equivalent to delta S equal to 0. Okay, so we can say that S1 is equal to S2. And we'll see how we can benefit from this definition in order to find what we mean by isentropic efficiency. So let us write first the energy balance. When you write the energy balance, Q dot is 0. You have a work produced by the turbine, so you expect to get W dot of the turbine positive because it's produced. And we consider the convention here because it's minus. Everything produced by the system is positive as work. Plus M dot H inlet minus H outlet, plus the change in kinetic and change in potential energy. Please, these ones are not always 0. So you should first write the whole equation. Then see in the problem if, for example, here, if you have the same cross section and it's a steady state, okay, then since the area is not varying and the velocity is the same, then you can consider that V1 is equal to V2. Okay, but if, for example, they gave you let's say the specific volume at stage 1, let's say, and the specific volume is varying from 1 to 2, then you should write the relation A1 V1 over specific volume at stage 1 equals to, because we have M dot N equal M dot out, equals to A2 V2 over specific volume at state 2. So in case they give you any information that shows that we have variation in velocity, you should write this relation to get what is the variation of V. And in case they told you neglect kinetic and potential energy, you can then simplify these terms. But if they don't tell you neglect them and you have information to calculate velocities, you should calculate it as in the exam. Okay? So here, when you drop these terms, okay, you get that W dot turbine over M dot is equal to H1 minus H2. And this is, if you want, the general case. It can be reversible, it can be irreversible. If it is irreversible, okay, we'll see that delta H will be smaller than delta H of reversible process. Why? To do the analysis why delta H irreversible is smaller than delta H reversible, let us write the second law of thermodynamics. Okay, if we consider the entropy rate balance for my turbine, the entropy rate balance is the following. First, it's a steady state. So So ds by dt is 0. This term is 0. It will cancel out. Equals to sum of q dot over t plus m dot Sn minus S out plus sigma dot. This is the entropy production, okay? And this term is 0 because we know that for the turbine, it's an adiabatic process, so this term will cancel out. What can you conclude then? You can conclude that since sigma dot is larger or equal to 0, then S2 minus S1 will be larger or equal to 0. If reversible process, S1 equal S2. If irreversible, then S2 should be larger than S1. And because for irreversible case, S2 should be larger than S1, then H2 should be also larger than H1. Yeah. And we'll demonstrate we'll demonstrate that delta H يعني مش هي ال H وهي delta H irreversible. هلا we'll see it in the graph. Okay, delta H irreversible will be then smaller than delta H reversible. Let us do the interpretation graphically to see this result. Okay, if you take the graph of the process that is happening in the turbine. What is happening in the turbine? We know that H is decreasing, okay, because we have production of work. So let us illustrate the process in HS diagram. You know that here we have reduction in pressure because as we go in the turbine, okay, the pressure will be reduced and H will be reduced. We know this, okay, but we can have this reduction in several ways. The first way is the isentropic process. Whenever you have isentropic process, S is constant. So if I want to illustrate this process graphically, I go from 1 to 2 with constant S, while H will decrease. Okay, so this is point 1, this is point 2. As you can see, H is decreasing. But here it's decreasing straightforward with S constant. And we'll see that it's impossible for H to decrease in this way, like this. Why it's not possible for it to decrease like this? Let me draw it here. Do you see the annotation or not? Let me 1 second. Is it possible for H to decrease in this way? Why it's not possible? Look at the graph. This is when you move in this way. This means that S1 is equal to S2. Okay? So for the adiabatic process, we should have for the isentropic process, this means adiabatic reversible, S1 should be equal to S2. Okay? And because we have demonstrated that sigma dot should be positive, then or equal to 0. And it's equal for reversible and positive for irreversible. If you have irreversible case, S2 should be larger than S1. And if you have reversible case, it should be just equal to S1. So it's impossible to have S2 smaller than S1. S2 smaller than S1 is impossible. This is why if you look at my graph, it's impossible to have S2 here. Because if S2 is from this side, okay, then it will be smaller than S1, which is impossible. So always, yes?
بقطش فكرة عيديز.
Sorry, do you hear me again? I was disconnected for a while.
Yes.
ممكن صوت ليش ما فيها تكون variating للتنميل.
Yeah, I will repeat it.
دكتور كمان
Yes.
لو عايزك في كتير بتعدي لي بس شو يعني ال 2S بعدني لهلا ما عم بفهمها.
اوكي
هذه
sure.
بنجيبها بار كالكول او
ايه وانا
أو
كمان.
شو فينا نستنتج يعني.
يلا راح اعيدها. اوكي ليكم انتوا اذا انا بعطيكم الانلت اوف ذا توربين، اوكي، إذا أنا بقول لكم steam enters the turbine at pressure 1 و temperature 1 مش you can go to tables and get all properties at point 1 يعني you can get
بلى
H1 you can get
و
S1
S1
okay
yes
great فأنتوا بس أعطيكم أنا state 1 pressure and temperature you can go to the tables and get all properties needed ففيكم تجيبوا H1 وفيكم تجيبوا S1 why you need S1 because if you know that the process is reversible ساعتها على exit of the turbine what should be S2 S2 should be equal to S1 يعني بس يقولوا لكم isentropic أو adiabatic reversible process يعني S1 is
2S
equal to
قصدك
S2 نعم
2S قصدك
ما
ولا
هي
S2
ليش بيحطوا لها S حدها ليش بيسموها بيحطوا لها S حدها هي الفاليو ل S2 لما يكون isentropic process اوكي يعني بيسموها S2S طيب فرجوك انه اذا isentropic process S2 will be equal to S2S بينما إذا irreversible process مجبورة ل S2 تكون أكبر من S2S. So in general S2 أو equal to S2S if the process is isentropic or larger than S2S if the process is irreversible. Okay? يعني إذا أنا بجي بقول لكم a turbine has an efficiency isentropic efficiency of 100% شو يعني؟ يعني عندي isentropic process okay so I don't have entropy production and if I don't have entropy production ساعتها بتصير S2 equal ل S1 بينما in real cases عطول في entropy production فحيصير في generation of entropy شو يعني؟ أو production of entropy مش نحن شفنا إنه for a turbine sigma dot is equal to S2 minus S1 okay وهيدي small larger or equal to 0 if reversible يعني إذا عندي reversible case دغري فيني أكتب isentropic process okay لأنه I have the case of adiabatic يعني Q dot 0 plus reversible I can say then that I have isentropic شو يعني isentropic؟ يعني S1 equals S2 اوكي ليش عم اقول لكم
و S2S كمان يعني
ادياباتيك ليش عم زيد انه ادياباتيك طلعوا بالفورمولا انتوا اذا التربين في كيو دوت بضل فيني اقول انه سيجما دوت هي بس S2 minus S1 يعني اذا ما كان ادياباتيك شو بتصير S2 minus S1 بتصير سيجما دوت بلس sum of Q dot over T اوكي يعني أنا إذا منه أدياباتيك ما فيني شيل هيدا الترم بس لأنه أدياباتيك بروسس بالتربين عطول عندي إلا إذا هن قالوا لي إنه في heat loss وعطوني إياه بس if they don't mention anything I can consider the process to be adiabatic so whenever I have a turbine and they don't consider heat loss to surrounding then it's adiabatic process بشيل هيدا الترم شو بيضل عندي؟ بيضل عندي what we call entropy production equal to the entropy change وأنا بعرف إنه الانتروبي production is always larger or equal to 0 أوكي يعني ما فيها تكون negative it's impossible هيدا الترم يطلع لي negative so S2 بتكون أو أكبر من S1 هيدا إذا كان irreversible أو S2 equal S1 وبهيدا الكيس بسميها S2S ليش بسميها S2S؟ لأنه هي السيمبل S represent إنه it's an isentropic process So ساعتها if I know that my process is isentropic, I directly determine what is S2S. S2S is equal to S1. Okay? And if I have irreversibilities, مستحيل مثل ما شفنا هون ما فيها S2 تكون أصغر من S1 مجبورة تكون أكبر من S1. So if you go to this graph, it's impossible to have the process like this لأنه إذا برسم البروسيس like this ساعتها بتطلع S2 أصغر من S1 and according to the second law of thermodynamics this is not possible يعني أنا I should be above this point تتكون S2 أكبر من S2S اللي هي S1 So S2 larger than S2S or S1 for a non-reversible process. Okay. And because S2 should be larger than S2S, إذا بتطلعوا بهالفيجر إجبار الدلتا H real يعني H1 sorry H1 minus H2 real إجبار تكون أصغر من H1 minus H2 isentropic. لأنه إذا باخد scale هيدي if I read H2S this is H2S. If I read H2 this is H2. طلعوا الفرق. H2 أكبر من H2S. So H1 minus H2 difference بين 1 و 2 real حتكون أصغر من ال ideal difference. أوكي؟ ونحن بنعرف إنه الwork W dot turbine over M dot real, the real case is equal to what? Is equal to H1 minus H2. بينما ال ideal case, the ideal case يعني W dot ideal case شو بنسميه isentropic أو فيكم تحطوا له S subscript S. W dot turbine over M dot for the isentropic case, the ideal case يعني for S equal constant S, you can just put S as symbol to say isentropic, is equal to H1 minus H2S. وأكيد مثل ما شفنا بالجراف it should be larger than the real W dot over M dot. Because this is always larger, we define what we call the isentropic efficiency. يعني أنا أوقات بالبروبلم أنا بقول لكم the isentropic efficiency is هالقد. Okay? So then you can relate the ratio because what is the isentropic efficiency? هلا we'll see it in the next slide. By definition, the isentropic efficiency is the ratio of W dot over M dot real over W dot over M dot ideal. Okay? So if we divide H1 minus H2 by H1 minus H2S, which is the case in the isentropic scenario, we get the efficiency. And of course, this efficiency is smaller than 1. It's between 0 and 1 because it's impossible to have delta H actual larger than delta H ideal. Okay? هلا we'll take an example to see how we use the isentropic efficiencies. And if we take, for example, if we take the following problem. Water vapor enters a turbine at a pressure of 5 bar and a temperature of 320 degrees and exits at P2 equal to 1 bar. We want to determine the work developed. The work developed is given. It's measured as 271 kilojoule per kilogram of water. We want to determine the isentropic efficiency. So here they want us to get what is the isentropic efficiency. Sometimes بالعكس بيعطونا isentropic efficiency and we find the unknown. Okay, we can change the problem, but the method is the same. All you have to do is to say that the isentropic efficiency is equal to H1 minus H2 over H1 minus H2S. Okay, how to do this? First, what do we have in this problem? We have water. Water. We know P1 and T1. We can go to the tables, okay, and we get H1. We have water vapor, okay. We go to superheated state. We have P1, T1. We get H1 and S1. Okay. Now, because they gave us, if you want, the work developed, we know it. W dot real, we know it. We just need to determine what? We know to get W dot ideal. Okay? W dot per unit, W dot over M dot real is given in this problem. The real one is equal to 271. What we want to search for, كأنه أنتم بتعرفوا H1 minus H2. Okay? Since you got H1, if they asked you for H2, you can find it because you know this. So you know this delta, which is W dot over M dot real. You just still need to determine what is W dot over M dot ideal, which is the case of isentropic case. Okay? Since you know H1, you just have to look for the value of H2S. And how to get H2S? You know that if I take isentropic scenario, what will be the value of S2? S2S is equal to S1. Okay, so I know that S2S is equal to S1. And if you want from my tables, what should I do? إذا أنا بعرف just S2, this is sufficient for me. يعني ليكوا هن شو بدهم منكم تجيبوا؟ بدكم تجيبوا isentropic turbine efficiency. You need H2S. If you just know S2S, it's sufficient to find what is H2S? No, you need two properties. What is the second property that you have? You know that the water vapor exits at P2 equals 1 bar. يعني now you have P2, you know P2, and you know S2S. Then you take these two variables and you go to tables. You say my only unknown now is H2S. Okay, I determine if I am in the superheated or if I am in the mixture case. If I am in the mixture case, I can find the quality and then find the value of H2S. Okay, so now once you do this, you can calculate the isentropic efficiency. Let us revise the method together. So the first way is to the first step